So this video is going to be an introduction to linear regression by example and is meant for those who are struggling to understand how the linear regression model works. The purpose is to introduce the basic concept in an intuitive manner by example. So let's begin. Consider the following scenario. Your supervisor asks you to price houses based on a set of features describing the characteristics of those houses. Those features are the number of bedrooms, the number of bathrooms, and the square footage of the house. We're going to use linear regression to perform this task. And the idea is as follows. We want to predict the price of a house based on the number of bedrooms, number of bathrooms, and the square footage. And the assumption that we will make is that there's a linear relationship between these features and the price of the house. It doesn't matter whether you understand this at this point or not. You'll still be able to follow along with the video. But basically this means that the addition in price to the value of a house given by one bedroom, or I should say given by two bedrooms, is twice as much as the addition in value to the house given by one bedroom. Same thing for the number of bathrooms. The addition in value that two bathrooms gives to a house would be twice as much as the addition in value that one bathroom gives to a house. So on and so forth with square footage. And we will illustrate that very clearly and using the math later on in a very direct and intuitive way. So we're going to create a simple model. And in our model, y is going to be the predicted value of the house. So that's going to be important. We're going to write it down. Y is the predicted value of the house. It's the value of the house that our model spits out. And we need to generate the model. Now, keep in mind that this value y, the predicted value of the house, is always going to be wrong because the model is trying to create an estimate for the price of a house. If it ever gets it right, we are very lucky. But in general, it's going to be wrong. But it's going to be hopefully close to the real price of the house. Now, let's start off with y equals, and now we have to figure out what the predicted value of the house is going to be based on some set of parameters, and those parameters are going to be the features of the house that we know. And so I'm just going to start throwing in some basic numbers to get us started. The first assumption I'm going to make is that the price of a house increases by $100 for every bedroom in the house. So let's add that to our model. So that means that the predicted value of the house is going to be $100 times the number of bedrooms in the house. So if we have two bedrooms, that would be 2 times 100. That would give us $200. And now I put plus ... because we got to continue building this model. So let's move on to the next feature, the number of bathrooms. And let's say that the number of bathrooms in the house will determine the price, and the relation there is that each bathroom increases the price or the expected price of a house by $50. So we're just now adding another term in here into our equation. So the predicted price of a house is going to be the number of bedrooms times $100 plus the number of bathrooms times $50. And now we have the square footage. That's what remains. So let's say that each square foot in the house is $2. Because let's say like a house can easily have 2,000 square feet, right? So now we have, and let's get rid of these equations because it's just getting repetitive. The predicted value of the house is the number of bedrooms times 100 plus the number of bathrooms times 50 plus the square footage times 2. And this is it. These are linear relations because we're simply multiplying the number of bedrooms or the number of bathrooms or the square footage by a fixed number. That's what it means to be linear. Now, have we missed anything? I think we may have. Let's assume that every house comes with a living room, a kitchen, maybe a garage, whatever. There's some set of baseline features that we didn't capture. So, and these baseline features are common to every house. So let's just add that into our model somehow. So those ellipses we're going to replace with $500. So now we're saying that the number of bedrooms times 100 plus the number of bathrooms times 50 plus the square footage times 2 plus $500 will give us the predicted value of a house. And that is it. This is our model. Whenever anybody says the word model specifically, this is in linear regression. This is what they're referring to. This is it. So now let's use our model to predict the price of a house. And keep in mind that our model is not perfect, and the only things that it accounts for are what we've included in here, which are the number of bedrooms, the number of bathrooms, and the square footage, and then some baseline for everything else that we're just, tacking on. So it's not a very complex model. It's fairly simplistic, but we don't want to get too complex here for illustrative purposes. So let's assume that we're looking at a 4-bedroom, 2-bathroom house with 2,000 square feet. So let's write that down. A 4-bedroom, 2-bathroom house with 2,000 square feet. What is our predicted value of that house? Well, we have our equation right here, and we can use that equation. So let's do that. Let's plug in some numbers. So I'm going to actually take this equation right here. I'm going to copy it. I'm going to paste it here. And I'm going to plug in what we know. So how many bedrooms are in the house? We said it's a 4-bedroom house. So where we have number of bedrooms, let's replace that with 4. How many bathrooms? We said it's a 2-bathroom house, right? So let's replace number of bathrooms with 2. And we said 2,000 square feet. So let's replace square footage with 2,000. And there we have a simple equation that we can now solve for. And what does this all equal? 4 times 100 is 400 plus 2 times 50 is 100. So that's all 500. So we have 500 here, that's 1,000. And then we have 2,000 times 2, which is 4,000. So 4,000 plus 1,000 gives us $5,000. Obviously, we're not going to buy a 4-bedroom, 2-bathroom house with $5,000, but this is what our current model predicts. It might be that each bedroom is more valuable than $100, and each bathroom is more valuable than $50. But that is it. We've used our model to predict the price of a new house. And this house was a house with 4 bedrooms, 2 bathrooms, and 2,000 square feet. And now our model has its limitations. We created a simple model that only takes these features as inputs. So these are the only features that we can use. And of course, there are many other things. Does the house have a pool? Is the house by a beachfront? and these are not going to be included in our model. But, you know, that is the limitation of our current model, and this is something you'll see in the real world as well. Your models are going to be limited for many different reasons. But okay, let's move on. And so let's consider, instead of a 4-bedroom house, a 5-bedroom house. How do we expect the predicted value of the house to change if now we have 5 instead of 4 bedrooms? Well, we said in the beginning that the price per bedroom, we fixed it as $100. That was what we did. So if we have one more bedroom, we expect the price to increase by 100. Let's check it out. Let's do the math. So again, we start with this equation. We replace number of bedrooms with 5 this time. Number of bathrooms, again with 2. And square footage, again with 2,000. We didn't change the number of bathrooms or the number of square feet. And let's calculate this. 5 times 100 is 500. So we have 500 here, 500 here, that's 1,000. We have 4,000 here, so that's 1,000 plus 4,000 is 5,000. And then we have 2 times 50, which is 100. So that means this adds up to 5,100. And that is by construction because of the way we designed the model. So the price of the predicted value of the house went up by $100 because there was one extra bedroom. And you'll see that the same thing happens with the number of bathrooms. If we add an extra bathroom, we would increase the price of the house by another $50. So let's do that. Let's take all of this and increase it by one more bathroom, and we have to put the number of bathrooms in here, right? Because we're following this equation. And this will give us 5150. You can pop that into a calculator if you need to. And so the relation that we're seeing between the number of bathrooms or bedrooms and the price, and how it goes up linearly, the price goes up linearly with these features, is why this is called linear regression. Okay, great. So let's, at this point, move on a little, and now let's look at how we can generalize our model. So the features of the house, by the way, I'm going to get rid of all of this for now. All of this, actually. Or let's just drop it down for now so it's not in our way. The features of the house, which are the number of bedrooms, the number of bathrooms, and the square footage, are also going to be the features in our model, which they were, right? And now we're going to look at how more mathematical notation would approach this. And we usually use the letter X for features. So let's do that. Let's give our features some letter names. So I don't want to have to rewrite this. We're going to copy and paste. Boom. Okay, so the number of bedrooms is going to be X1. The number of bathrooms is going to be X2. And the square footage is going to be X3, as you see here. And each one of these is a different and unique variable. So X1 is its own thing, X2 is its own thing, and X3 is its own thing. So now let's rewrite our equation using the new names for these features. So now we have y, which is the predicted value, is x1, where x1 is just literally the number of bedrooms. So again, we can, from our previous example, if we had a 4-bedroom, 2-bathroom house, we could plug 4 in place of x1, 2 in place of x2, and 2,000 in place of x3. And we would be able to do the same calculations that we did before. So all we did here was replace words with letters. Let's do the same for what we had as the price for each bedroom, for each bathroom, and for each square foot. And this can also be stated as price per bedroom, price per bathroom, and price per square foot, which helps, in understanding why the mathematics works the way it does. Because you multiply the price per bedroom by the number of bedrooms, and that gives you the total price factored into our model for bedrooms. So let's do it. And the generally used letter, Greek letter here is beta. So we're going to replace the price, we're going to replace the price per bedroom, which was $100, with beta 1. We're going to replace the price per bathroom with beta 2, and the price per, this is a typo, per square foot with $2. Okay, so this is just a replacement. So let's do it. And here we have our new equation. x1 beta 1, x1 times beta 1 plus x2 times beta 2 plus x3 times beta 3 plus 500. And remember, this equation is the exact same thing as this equation. We're just using different terminology. That's it. And that's what we're walking through right now. So beta 1 is $100, and x1 is the number of bedrooms. Same thing for x2 beta 2 and x3 beta 3. Now, the one thing I didn't do yet was our baseline costs. So our baseline costs get a special place as beta 0, making our final equation this: x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus beta 0. And sometimes people prefer to use this notation, beta 0 times 1. But it really doesn't matter. Beta 0 or beta 0 times 1 is the same thing. So let's just leave it out. Okay. And there we have it. We've taken our initial model and we've kind of generalized it with some, Greek letters, some variables, we should say. Now, this is what you'll generally see when searching online. This is the notation used in linear regression. And now let's dive a little into why they're used. So in order to do that, I'm actually going to step away from this notation. So this is our model. This is also our model. So I'm going to use this form of our model to explain a little further. Here in our model, we arbitrarily chose a price per bedroom of $100, a price per bathroom of $50, and a price per square foot of $2. But arbitrarily chosen prices are of no use to us. Our objective is to somehow use math to come up with these numbers, because we can't just pull them out of thin air. We have to use the data to determine these numbers. And that is the magic of linear regression. So we want these numbers to be as close as possible to the reality. And the data can help us figure out what that is mathematically. So remember, we started off with our supervisor asking us to produce a model. But any good supervisor would make sure that you have the data necessary to do so before requesting such a task from you. And having data is essential to the whole process of linear regression. In our case, the data will be of houses and must include the price, the number of bedrooms, the number of bathrooms, and the square footage. So our data has to include our data is going to include a list of houses, a list of many houses. And for each house, we need to have the true price. We need to have the number of bedrooms. We need to have the number of bathrooms, and we need to have the square footage. So now what you see is that in our model, Y was our predicted price. But we want our model to learn in the future, and it's going to learn how to set these numbers, the price per bedroom, the price per bathroom, and the price per square foot, and the baseline costs based on the real data. And it's going to have to know what the real price is. And the real price is the analog to the predicted price. The number of bedrooms, obviously, would be similar to what's in here. Number of bathrooms, square footage, meaning that we'd have a list of many houses, and for each house we'd know all these values, but we wouldn't know what the price per bedroom, the price per bathroom, and the price per square foot are. And that's what we need to now plug in. Sorry, we're not plugging that in. Our model will mathematically deduce the best values, as well as the best value for the baseline costs. So really, these values are what we want to figure out. And these values, these highlighted values, are actually our betas. Beta 1, beta 2, beta 3, and beta 0. So given a data set with prices Y and feature values x1, x2, x3, we want to figure out what the best values of beta are. And so that's it. That is what linear regression is. There's a lot of math behind figuring out the optimal values for beta, but that's beyond the scope of this. Hopefully you now understand what the model is. This is the model, and this is the model, both written in different ways. And then you optimize the model to figure out what your betas are. All 4 of them in this case, but there can be much more. All right, thank you for tuning in.